Yes.
I can just do it off of the thing, and then we can switch them.
Yeah, I think he was saying that he's running this one. Then he's gonna switch it over to mine on both.
Okay, I'll just do it. I'll just
So
do that then.
do you want to give it to him? And you'll put it
It's
put
right
him up
here.
right on here.
They're already here.
Okay.
Yeah.
Yeah, he's gonna switch it.
Okay.
Now, how did you end up at Mitre? Get recruited or referred? No, it sounds good. So it's a government scholarship program, specifically focusing on people interested in security.
Hey everyone, hope you, oops, sorry, that was super loud. Hope you found everything okay. We're going to go ahead and get started. So if this is your first time, welcome to Mitre Tech Talks. Tech Talks are monthly technical topics that we discuss. Our engineers come. I'm butchering this pretty horribly. We have monthly talks where different engineers come and talk to you about cybersecurity topics that we do here at Mitre. So tonight we're going to hear from Mark Ida, but before that, I'm going to give you a quick overview on what Mitre is.
We're Mitre.
Or not.
We're Mitre, and we're solving for a safer world by tackling the kinds of problems that no one else can solve. The really big problems, the internet-sized problems, the landing 87,000 planes a day safely type problems, the kind of problems that take data scientists, system engineers, economists, geologists, healthcare experts, and joint mission simulation labs to solve. Safer by solving important problems, like figuring out how to crunch a petabyte of data to identify a rogue pharmacy that's filling fraudulent prescriptions, and then connecting the dots to see how that might be a key to solving the opioid crisis. Safer by solving complex problems, inventing things like new GPS signals, which becomes foundational technology for pretty much everything, and then reinventing navigation to be less dependent on satellites and more resilient on the battlefield, more accurate on the runway, and safer just about everywhere you go. Safer by solving all kinds of problems, whether it's making sensors more affordable to deploy, your credit cards and electronics harder to hack, or underground drug trafficking tunnels easier to find. That's because Mitre is about sharing, not silos. We bring together industry experts and government agencies and academia to achieve a unique vantage point, to find answers, inform new policies, set new standards, and scale it up big so it makes even more people's lives safer every day. You can't count on a startup or a Fortune 500 company to do that. You need a company like Mitre, because we're not just any company, and we're not in it for profit. We're a strategic partner that applies science, technology, and systems engineering to take on society's most pressing challenge, to make the world a safer place. We iterate, we invent, we model, we discover, we create, we lead, and then we share the answers. That algorithm, those prototypes, that 3D print your own drone in the field kind of solution, so that government, private industry, and the world can put it to use for the common good. We're Mitre. We solve problems for a safer world. Your world.
So that video flashily summed a lot of it up, but I'm just going to go through this really quickly. So Mitre has been around for a little while. We are working in the public interest, as it's mentioned. It's one of our little catchphrases, working in the public interest. We are a not-for-profit, so we don't make money, and that kind of helps us be able to provide an unbiased opinion. We operate 7 FFRDCs. It gets a little bit complicated. We have flyers on that, but essentially we are not one. We help run them. As I mentioned, we've been around for a while. We've contributed to several different areas of engineering, and we work to support the public interest. Some of our capabilities listed here include critical problem solving, social sciences, systems engineering, and tonight you'll be hearing about cybersecurity. This has to be wrong because we have a lot more employees than that now. Around 8,000, maybe 9 now. We have a high focus on higher education, so we have programs that support you getting a master's degree or a second bachelor's or even PhD. There are people who have been here for as long as I have been breathing, and there are people who have been here for 3 or 4 years like myself. So that was a quick overview on Mitre. If you have any other questions about that or working here, you can find me over at that table. But right now we're going to hand it over to Mark Guido, who's going to talk to you about periodic mobile forensics.
Okay, can everybody hear me? All right, so my name is Mark Guido. I'm a department head here in the Cyber Operations and Effects Tech Center. But before I was a department head, I was a principal investigator for an internal R&D project called Periodic Mobile Forensics, and that's what I'm going to talk to you about today. So before I go into periodic mobile forensics, I just want to kind of level set the topic area. So, how many of you, show of hands, do digital forensics on a daily basis? Anybody? Okay. How many of you have heard of the San Bernardino iPhone and the FBI wanting to compel Apple to help them to decrypt the phone and in order to get the contents? Okay. So I don't know if you've seen, but actually the story on the right is back in 2016 for the San Bernardino iPhone, they actually the FBI the case was dropped against Apple, and so that just kind of postponed what actually happened about 2 weeks ago. The FBI again has been trying to push Apple to help them decrypt the phone for the shooter, the Florida shooter. So this is happening, and Apple is putting up another fight. So it's not as easy as just what we saw, what we saw in the news. Apple can't just unlock the phone. What the FBI wanted to have happen was that Apple helped them to get into the phone, and then once they were in the phone, Apple had to try to find a way to get the contents of the phone off of the phone so that it can be analyzed forensically. Okay, that usually takes a set of privileges on the devices that you don't normally have. As a matter of fact, Apple and on the Android side, all of the Android vendors, they actually make it very difficult to get the privileges that you need to lift data off of the devices. And then on top of there, once you acquire that data, you have to go through and analyze it. And so we're going to talk more about this, but the thing that the FBI really wants to get is they want to try to get a bit for bit copy of the device. They want to get all of the data that they possibly can get off of the device. And the reason is because forensically, there could be data all across the device. And so if you don't go and get all of that data and then analyze the entire device, then you could miss something. Okay? So these are just two cases, but in actuality, this happens all the time. There could be cyber investigations that involve phones. There's been a lot of cyber investigations, and a lot of times the investigating agency may not be able to fully get into the device. And so this is part of what periodic mobile forensics was trying to address. All right, so what is periodic mobile forensics? Well, I told you it was an internal R&D project. So it was research that was trying to apply traditional and mobile forensic techniques towards the monitoring and analysis of mobile devices. So this is just a little history. We've been doing this since 2012, and in 2013 we actually published a journal paper where we were analyzing malware at that time, malware on various phones. Then in 2016, we ended up putting out, we kind of changed our focus, and we put out another journal paper on rapid imaging, okay? And we're going to get into some of the rapid imaging pieces tonight. And then in 2017, we ended up doing a very large experiment out at Purdue University. And we actually had various students, that they were volunteers running around Purdue University, and we were collecting data while their phones were in their pockets. And we ended up analyzing that data that we got back, and it turns out that we were able to collect it like this. We were able to collect the equivalent of, we collected over the course of a semester, the equivalent of 1,100 images. That is, if you figure that out with the size of an image, it would be about 17 terabytes worth of data that we collected. But we're going to show you that a lot of what we're doing is to make this process a lot more efficient. So that equivalence, we ended up getting to the point where our database was a lot smaller. Of that data, it was about 300 gigs is all the data that we needed to collect in order to be equivalent to that 17 terabytes of information. So what happens when you collect a lot less data? Well, you're able to move it around a lot faster. You're able to analyze it a lot faster. You're able to just do things a lot faster. And so we're going to get into why this happens with periodic mobile forensics. Just one more thing to note on here. We applied for a patent, and we were granted a patent earlier in 2019. So this is a patented process that we have.
Excuse me.
Yes.
In terms of terminology, when you say imaging, is it from the live disk or from the dead disk?
I'm sorry, can you come over to the microphone, please?
When you mention imaging the device, is it imaging the live disk or imaging the dead disk, or does it matter at all or not?
So that's an interesting question. If we can, the better thing to do would be to image a dead disk. But in the mobile world, a lot of times you're only going to have a live disk to be able to image. There's actually litigation that they allowed, and it was admissible in court, phones that they were not able to grab the entire device without changing the data, and so they actually changed it while the phone was operating, and they still allowed that data in. The rule of thumb is you try to change as little as possible on the device. But what I am talking about is I'm trying to get at all of the bits across the device storage. All right, so that getting all of the bits across the device storage, this is a great lead-in, thank you, is called physical acquisition. So there is such thing as a logical acquisition, but a logical acquisition in forensic speak is when you go in and you pick out various pieces. It's easy to miss things if they're not in the place that you expect. So we want to try to get a physical acquisition from the device. Okay? So various tools are out there. There's a whole commercial market space. These tools, they go through and they do a traditional bit-for-bit copy. They will try to access a bit on the device. They're going to send it over the USB, and they're going to collect it on some connected device. Okay, so it works very much like this. Here's the traditional method. Okay, so we have a block device. We're going to start looking at the first bytes, and then we're going to walk through the phone from beginning to end. Now it assumes that we have the access to be able to do that, and then it's going to walk from beginning to end, and it's going to send that copy over a connected USB cable to some collection station. All right. So what periodic mobile forensics uses is it uses a concept called differential forensic imaging. Differential forensic imaging works kind of like this. If we know a little bit about what to expect at these areas of the device, then what we can do is we come up to the first block in the device, and we see that we already know about it. We don't have to send that block across the USB connection. Instead, what we're going to do is we're just going to send a little message that says, we already know what this block is. This is the starting block. We're going to iterate through the phone, and on the second one, we've never seen that data before. Okay, so we're going to send this one across the USB connection, but we'll iterate through the phone all the way to the end, skipping blocks that we know about. Okay, this is just a paper that describes differential forensic analysis. Okay, so how do we put this into practice? All right, so we've put this into practice in a variety of use cases. So we have, like I said earlier, we started out in the enterprise looking at malware on phones, and we also looked at that Purdue experiment. We looked at masquerading users. So a masquerading user is somebody other than the device user utilizing the phone. So the Purdue experiment, we tried to show that we could identify a user that may not be the actual device user just by their behaviors on the device. And so we used some machine learning, and we compared various machine learning classifiers, and we ended up getting very accurate results to show that it may have been the device user, or it may have been a masquerading user. So a masquerading user, the classic example is you leave your phone in a hotel room and the evil maid comes in and gets at your phone and changes it. But I always like to tell the story of I came home one day and I put my phone on my counter, and my son came and grabbed my phone, and he put on the snow cone making app. I don't know why you need a snow cone making app for my phone, but he put it on there. Now he bypassed all of the security that was on there, and putting it on there, he was able to enter. So the idea behind masquerading users is identifying that it's actually my son using the phone, and then taking action from there. All right, we're going to go into the rapid acquisition piece. This is where the primary use case would be like a crime scene. You need to get at the data, and you need to get at the data. You've never seen the phone before. What do you do? Forensic laboratories, we have various imaging pieces, and then analysis. Device imaging and re-imaging, we've actually been able to take data off of the device and put data back onto the device and make the device start up and utilize that. Analysis, device and app exploration, and then low bandwidth communications. So what if we aren't dealing with devices? What if we're going to do an efficient process and we're going to try to use that for communications instead of acquisition in this case. And then finally, we're going to talk about mission validation a little bit. Mission validation or change detection is our implementation does something a little bit different than everybody else in the market space. And it allows us, because it works different, we use that differential forensic imaging. What it allows us to do is it allows us to, if we could see a device twice or more, we could take a before image and then an after image, and we can compare those two together. All right, so let's jump into the rapid acquisition, because this is kind of where we get very where our research gets very interesting. So we had a bunch of sponsors that we were doing work for, and those sponsors had a couple of problems with the commercial space. Number one, their phones that they would plug into these commercial vendors' tools, sometimes the phone just didn't work. So that has to deal with the acquisition method, or the access method that you're utilizing for that particular device. So these various vendors, they compete against each other. Who's got more acquisition method or access methods? So that is one piece, is how do you get that access and that privilege in order to run these things? And then the other problem was it just took too long. Maybe there's not enough time. Maybe it's a very time-sensitive criminal investigation that you need to try to get at that data. Even the San Bernardino iPhone, it went on for weeks where they were trying to get access to this phone, and that the investigation is still going on. They're trying to answer those questions. In some cases, there's an immediacy that they need to try to overcome. So basically, can we do this in 10 minutes or less? Was our goal, and the answer is yes. We were able to take acquisitions, and we were able to get down to 10 minutes. How we did it is you got to gain that access and privilege, okay? And then afterwards, we're going to get speed gains by doing a bunch of efficiencies on the through our algorithm. All right. So the first thing I want to say is we have some derivative research on the access methods onto devices. So this derivative research looks at how do we get onto devices to prepare them in order to do what we need to do on the devices. So there's basically three methods to get onto the device. There's the bootloader method, which would be connecting to the device in bootloader mode and interfacing with the device, being able to pass over various code and then run it onto the device. This is very hard, but it is the preferred solution. There's putting on a custom recovery. This is where we're actually taking a recovery image that runs on the device, and we're putting on a new image that we control. So we're able to use that image to allow us to get privileges. So some phones are locked so that you can't do this. I'm sure that you guys have heard of carrier lock. Carrier locking? Okay, so that's not the locking I'm talking about. Some phones are bootloader locked, where you can't write over certain parts of the bootloader because there's the trusted boot chain. So these are some of the things that you need to overcome. And then finally, if the phone's running normally, more of a live phone, can you escalate your privileges to the point where you can run and touch the block devices that you need? So those are the three methods, and there's various these vendors, they all compete against each other to try to find all of those access methods. On the Android side, there's so much diversity in the market space that you really need to keep track of for a particular phone. How are you going to be able to access it? This number one, while it's the hardest of all three, it is very specific to the hardware that you're working on. So you have a particular phone, and the last I checked, there was about 15,000 Android models in the market space. So you think of the complexity of the problem there. It's very hard to do, and you may not be able to get into that many devices with it. But it is the preferred method because it gives you the most access. And just like you were talking about, you're now dealing with a dead disk. You're running essentially your custom code on the device. So the device is not starting up all of the various tools and capabilities that usually it is in normal mode. Now, something has happened over the past few years that has really made the number one, bootloader mode, and the number two, custom recovery mode, that much more difficult. And it's the increase in the complexity of the hardware-based encryption that is used on devices. So hardware-based encryption, a lot of the phone is now encrypted. And so even if you get in and you get access to the bootloader where you can run your code, a lot of times the device is encrypted. So you have to try to figure out how to work around some of that encryption. All right, so the second piece of this, once you have access to the device in some way, is we said we want to escalate our privileges, and then we want to run an efficient algorithm. We use an agent that we put onto the device. We only put it on temporarily. This agent goes on the device. We originally wrote it in C, and then it's been rewritten into Go. But it's basically an executable that runs on the device. It utilizes our algorithm, and it also uses a bunch of efficiencies that we'll go through, some speed improvements. So the USB connection is a lot of times the bottleneck. You're trying to pass a lot of data over the USB connection, and so you got to wait. A lot of the vendors, if they're taking a bit for bit copy, they got to sit there and wait. And a lot of times, anybody fill up a phone with 100% with data? What happens to the phone? Does anybody know? It doesn't work, right? It doesn't work. It's painful. You got to try to get your data off of the phone in order to get back to be able to use the phone again. And it ends up being very painful. So inherently, because of that, a lot of our devices, everybody's walking around with a little bit of storage, at least a little bit of storage that's not filled up on our phones. Or else we'd all be complaining that our phones are full and they aren't working. So when these vendors go and they're trying to send a forensic image across that USB, they're actually sending a lot of null data, a lot of blank data. So we're going to do some efficiencies to not have to send that blank data. So that's our first improvement. We're going to skip those zeros. Okay, if we can identify that there are zeros in a particular block of data, then we don't have to send them across. We just have to send a little message that says this block of data is zeros. So how do we identify it? Well, we could take the entire block of data and we could use a hashing algorithm like MD5, and that MD5 algorithm will come out and it'll hash to a particular hash. And then we can compare that hash, and we can see that it's all that it matches and it's all zeros. But that's not as efficient as we can be. Instead, what we do is we iterate through and we start with the first bit, and we say, is that a 0? Yes, it is. Let's go to the second bit. Yes, it is. And we completely iterate through that block of data. If we hit a 1, then we exit out right of that. And we found that this is actually 250 times faster than your most efficient hashing algorithm, MD5 on all of these devices. Okay, so speed improvement 1, we're not going to send any zeros. Speed improvement 2, we have a hash list that we pass over to the device along with our agent. That this hash list has a bunch of representations, hashes, of data that we know about. So when, if you take a Samsung Galaxy S10 or Galaxy Note 10, okay? A lot of that data is the same across multiple people that have that device. So if we have that data already, if we know about it already, why do we have to send it across the USB connection? Why don't we just match that data and just send a little message that says it matches data X? And so we're going to speed this up a lot by not having to send all of this data across. So this gold hash list is it's basically representations of the data that we know about. Yes. Can you step up to the microphone, please?
There are tools to do the image analysis without you do this kind of a hash to know what's the data in it. Pro Discovery, FTK, data access, several tools.
So we can use previous data that we know about across, for instance, across like devices. We could use data from the device itself, and when we're iterating through the device, we can build that hash list and add to that hash list so that we aren't sending anything twice. But the bigger thing is if we know that our target is an Android phone, there's going to be some data that's alike on multiple Android phones. So if we pull in a bunch of representative images into our system, and then we create a hash list, then we're going to match on things. And we don't have to be 100% correct, 100% matching. We just have to be good enough in order to get a speed improvement. Does that make sense?
If the data is not encrypted, you can just load up the whole things. You can see them with it will including if you have a hexadecimal whatever kind of image. You can choose different kind of conversion. It will show user-friendly ASCII character sets. That's how I taught digital forensic courses before, and we use all kind of a digital forensic tool to analyze data.
Yeah. So one thing to mention about this is you can hash a whole lot of things. You can hash files. You can hash. You can actually get lower than files. And what we're trying to do is we're taking a block of data, and that block of data, we're trying to hash that. We aren't trying to deal at the file level because files could be in different places on your device. But if we take blocks of data and these offsets, we can compare this block of data that's on phone A with block of data that's on phone B. And if they are alike enough, then they're going to match. I can at the break we can talk a little bit more. Yes.
In terms of the use case of this, there are two scenarios. One is that the device is captured for analysis. So you have the physical access to the device, and you want to capture the image and do your digital forensic and do, infer any information that is in the disk. And the owner of the device doesn't have the access to that. So that's one scenario, which is the traditional way of doing that. The other way, if I understand correctly, is that the owner is actively using that. And then basically you go and hack the device and install your agent, and you actively sniff out the image. Is that the correct assumption?
Well, rather than say hacked, why don't we say instrument the device? Okay. And that is exactly what we did for the Purdue experiment. Is we ran it while the phone was live, and the user was using the device, and we were operating in the background. So that is one way to do it. A lot of what I'm talking about tonight is actually the first way that you're talking about, where there is not enough privileges, and you need to get at the data to, for instance, assist law enforcement or some other scenario like that, and you got to try to get at all the data on that device, and you have to do it as quickly as you possibly can.
So for the second scenario, if the user using the device while you capturing these images, isn't it intrusive enough so that you flag the user by doing this and the user notice these activities in the device? Actually,
for the Purdue experiment, we were able to operate completely in the background, and users, the volunteers of the experiment were told there was some deception that we put in our experiment. We didn't actually tell them what we were doing, and the users did not notice any activity on the device. And we sent the equivalent of 1,100 images off of the device while the users were using them. So you can be rather stealthy on the device and not manage the resources so that users don't actually notice it.
All right, thank you.
Excuse me, please come up to the microphone.
What I'm saying is that 1,100 images is per device? 1,100?
No, per device, we were basically collecting the equivalent of one device a day. Mm-hmm. So we had devices. It went over the course of a semester, and we had 1,100 images across 35 devices. And so we had a device with like 125 images or something like that was the most. But sometimes some of the transmissions wouldn't always make it, and so that's actually the reason why our original research was called periodic mobile forensics, because periodically we would try to send again. Sometimes phones just are offline. Sometimes when we were transmitting, somebody gets into an elevator and the transmission breaks. So we would pick it up and try to send again. And if the phone is off, the phone goes through different states. Sometimes you can look at a phone and the phone looks like it's off, but actually there's background processes that are running. That was what we were utilizing to continue operating while the user thought that the phone was essentially off. It's called a wake lock on Android devices.
There are free software you can remove, snap an image, any kind of devices, as long as it has the internet connection, has the IP address, you can snap an image, and then you can use another free tool to do analysis of the whole image, including operating systems. Usually as a user, I cannot see what operating system see, but with that kind of snapshot, you can see everything, including what operating system can see. Those are very, very easy to use. we taught that in the class.
Let me know what programs you're. Yeah, so DCFLDD is the way that works is you still first have to have access to the image, and then DCFLDD will do that full forensic image that I'm talking about, the traditional method. They will walk through. Now you can have a break in transmission, and DCFLDD will pick back up, but DCFLDD is one of the things that I'm going to get in, and I'm going to show just the difference in efficiency that what we're doing compared to something like DCFLDD. Okay. So the third improvement is, turns out we don't have to hash the entire device. So for our second improvement, we were saying we're going to pass a hash list over, and then we're going to compare the entire device to that hash list. Okay? What if we didn't have to hash the entire device? What if instead we pass over two hash lists? The second hash list is a hash list of just the beginnings of blocks, a small amount of data that you can match very, very quickly. I don't know if you've ever tried to match a hash, but if you're dealing with a large data set, a large block of data, and then you try to compare that to the hash, it has to go through and it has to calculate the hash of that large block of data. It takes a little while to do it. What if instead we only compare it to the beginning, and we have another hash list that has only got those beginnings? So what does this tell us? Well, if we match that hash, meaning that we've identified data that we potentially know about, then we got to hash the rest. But what if we don't match that hash? If we don't match that hash, we know we got to send the data across the wire. We know that we haven't seen that data before. So instead of hashing the entire phone and utilizing all of that processing power, which on phones typically they've been a little limited on processing, instead of doing that, let's send the data we don't know about, identify it, and send it right away. And then the data that we do know about, we have to hash the rest. And what ends up happening is we get another speed boost going through this. All right, so just how fast did we say we went? So there's our PMF in 10 minutes. I'm being very nice to all the vendors that were in the market space at the time. This was in August 2016. We did this for our paper. In actuality, PMF was faster than this, but I'm going to give it 10 minutes. Okay? Now, I'm not trying to be a joke here, but we're gonna see how fast this is on this scale. The only one that when we're talking about 60 minutes at the time. By the way, does anybody recognize that phone? The acquisition time for a 16 gigabytes Galaxy S3. That's actually the phone that Donald Trump was using when he became president. All right. So this is an old phone. It's an old phone. It's a slow phone. Okay. So in 2016, August 2016, the MSAB XRY, one of the top vendors in the commercial space, they were about 55 minutes to take an acquisition of that device. They did that traditional method. We were less than 10 minutes, and we came out with equivalent data. All right, they're the only one that made it on this first page. Let's go show. All right, so now we have, let's see, oxygen forensics. They made it on there. If you notice in the beginning when I showed that timeline slide, we've actually licensed our work to Oxygen Forensics, and they've built in a module into their tool in order to achieve speeds like we're getting. So Oxygen Forensics has added our stuff to their product. Celebrate makes it on here. This is the Celebrate UFED for PC. It's the PC version of it, where they're able to take advantage of the additional processing power of the PC. All right, but that's what, 120? That's 2 hours that it takes, and we're still going. All right, so now we have Celebrate UFED Touch. Now that's the handheld imager. And we're close to 3 hours, right? Yeah, we're just about at 3 hours on that. And then DCFL DD, or an equivalent DD and Netcat, we took this as just a baseline, and that took us almost as long as Celebrate. And Celebrate's basically leading the commercial market space. So you see what we can do when we're putting these efficient practices in place. Now, since in the last 3 years, the commercial market space has tried to speed up. Celebrate has actually put out an update to their tools that I like to say that it was because we were putting out our paper and publishing our results that the industry recognized that we had to get quicker. And so this is some of the reasons why we do research, is to influence the industry to try to incorporate some of these into their products. We are still quicker than Celebrate's fastest, so that's a good thing. Did you have a question?
Yes. So going back to the partial hash blocks, so what is the likelihood of getting a false match? Because since you are only looking at like the first blocks, wouldn't that reduce the hash space? So if we don't match that, we know we haven't matched the rest, so we send it right away. Okay, we send the whole block right away. If we do match, then we got to hash the rest of it. And programmatically, the way that we can do this is it's actually very, very nice, because we don't need to start over and start calculating a new hash. You can actually add to your hash that you've already calculated, your space. And so we do that very efficiently. We just add to our space to get up to the full block. But in terms of false positives, it's non-existent for this part. We're either sending or we aren't sending. Now there is something that could happen where we get the data back at the database, and maybe we've already seen it. Like if the device, it's possible because of how we're doing it. If we sent 2 copies of it to the server. But the server is going to add it to the data that it knows, and so it's only going to add one copy of it and then throw out the other one, and so this does happen very, very quickly. The problem and the slowdown is when you're talking about doing it across an entire device. We're talking about one little block that we may have sent it twice, and the server ends up filtering it out. Makes sense. Thank you.
All right, so I've talked a little bit about just how fast this is, and I mentioned earlier that we're going to be even faster if we've seen a block twice, or if we've seen a device twice. Okay, so this is the mission validation and the change detection piece. What we can do is we can take an image before, and then we can take an image during. The phone is used during something, and we take that image and we compare it to the first image. Well, that second image, we've already collected a lot of data on the device, and we've identified it, and it's now known to us. So when we take that second image during, we don't have to collect all that data that we know about. We're going to match all those hashes, and so the only thing we need to pass back on the second image is the change data on the device, so it means that we're going to be that much quicker. Whereas I said I'm going to be nice and say that we were 10 minutes on the first run, the second run may take 5 minutes, may take 3 minutes, and you're going to get subsequently faster as you know more and more data. That's actually a nice side effect of our tool, and then you can take an image after, and you can do that same comparison. You can compare it all the way through, and you're only looking at, and you're only grabbing and acquiring the change data. All right?
Mark, I have a question. Are there privacy issues involved here?
So I really didn't want to get into privacy issues. When we were talking about the San Bernardino iPhone and Apple and everything like that, there obviously are privacy issues that are involved in here. The way that we would use these types of technologies, though, is potentially to assist law enforcement or for a military application. There's privacy implications for using this, but it really comes down to whether that data needs to get in, whether you need to get at that data. So I understand the privacy implications of Apple not wanting to help out the San Bernardino iPhone, but at the same time, there's a bad person who did a bad thing that data could assist in resolving the case, and so there's all those considerations that you need for all of this. This is an inherent issue with digital forensics. All right, so what does this all look like? So we can either be spread out and have our components on a bunch of different systems, take advantage of a laboratory network, take advantage of the resources, or that entire blue space can be on this one device, this one client, and we can operate in this mode. Okay. Now, one thing to see is that part of our efficiency allows us to operate across not one device, but the entire USB space. So if you can connect up a device and address it in the entire USB space, then we can theoretically operate across that entire space. So I've got one USB, one bus up there. That's 127 devices that you can theoretically connect to. Now, in practice, we can't connect to all 127 addressable devices on commodity hardware. You end up having power problems. It has nothing to do with PMF. It's that when you start flowing over that bus, you have to manage the hardware, manage the power for all of those devices. There are hardware solutions to combat that, and I have seen 256 devices connected to one system at the same time. So what we were able to do is apply commodity hardware to see just how fast we can go. And so I have a little movie, and then we'll take a break after this. So I'll leave you with the movie. Okay, we're gonna acquire 20 devices as quickly as we possibly can. after 2 minutes, he was able to acquire 1 or 2 devices. He's swapping devices as the first devices get finished. So the cool thing is that we learned a lot from those first devices. So as we applied it to the next devices, we were able to take advantage of that speed improvement. And so, I guess we're not fast enough. I got to continue talking until we get to 15 minutes. Can you step up to the microphone?
have a great rapidity of capture, but what about the analysis side? Because that is stuff.
Yeah, so the analysis you can take advantage of the same thing. We do have a whole analytical side to what we did. Especially, I mean, you've heard a little bit about it, the analytics that we did during the Purdue experiment. We actually have a whole detector architecture where these are tiny little forensic processes that you can run on our captures that we make, and you could have user-defined captures too. But I'm not going into a whole lot of the acquisition or the analysis piece tonight. I have a bunch of slides on it, but where I was trying to focus on the speed improvements that we were making here. If you want to, you can get my information, and I can point you to some public released material that we have. Yes, can you come up to the microphone? And we're going to take a break. We're going to take a 15-minute break after these questions.
In this demo that you mentioned, the speed improvement, I'm not getting that. The capture that you get is from the static state of these devices.
Correct.
Right? So the differential imaging that you get doesn't give you any speed improvement, right?
Yes.
Because the next time that you capture it, the state of the device is not changed.
I know, but we were able to take advantage of those like devices that were connected. So the first device that we ran through, and we learned about what was on that first device, we were able to take advantage of it on the 11th device that we plugged in, and the 12th device that we plugged in for the data that was the same across those 2 devices. And we were able, so we learned from that first device in order to apply it to the 11th device, and so on. And every time the device is finished, we added all those hashes that we learned on that device to our hash store, so that the next device that we ran would get at all of that data.
So your repository of the collection that you get is shared across all the devices? Is not specific to one device?
Yes, we will work across an entire repository, an entire set of devices, and all of their data goes into the same database. Now we can break it up, but you're not taking advantage of the data that you know in that case.
I see. All right.
So we can go either way. I mean, some of our sponsors, they may have to have separate databases for various investigations that they may do.
Thank you.
All right. I think we're at a 15-minute break.
I think this is for the larger
Oh, okay, okay.
Yeah, that's easy. Just kind of hold it down. Sure.
Are you actually, okay. I actually don't have any place to write it down. We've actually got some other better support out there. We stopped supporting guys a few years ago, and so it's never been updated.
Yeah.
So I don't think we can afford it.
Thank you so much.
Do you know Christmas? He's been the leader, lead out there for some of the other groups that are more starting. It's actually changed a lot.
Yeah.
So it's not entirely as usual. But well, the whole marketplace has changed. When I was talking about the access devices, there's ways of doing older devices that now we have to do some. But we like to do it first one and the second one, and those are the phones for mission navigation pieces like that. They're actually stopped with us. Okay. Yeah. Ryan. Yeah.
Those in the video,
Some of them.
well, like, were they all access through like so many more
They're all in English.
well, they're all kind of like
No. Some of them.
well, if they were all like threes, those kind of the first two.
Right, so we're gonna get. But what about and if let's say you have a game thing, let's say you are a local say you've learned about it in New York. It's by each year for those 4 people. We're gonna be able to instead of taking that one and applying that movie again, we're gonna apply it or application. You're running across the enterprise, other people that say, no, I agree. We only see it once.
Yeah, and I'm not technical, but go on. Yeah. Yeah. I guess you can install it remotely, right? It gets into that gray water, gray area, what's legal, illegal. I think so. That's right. This is why you don't know. It's open source.
Okay, we're going to get started in one more minute here.
All right. What we're going to do is we're going to go into some limited resource environments and how PMF can be applied to limited resource environment. Oh, I'm hitting the wrong button. Okay. So let's go back. Let's go back to this picture, and So a lot of this, you might want to throw some hardware at this and get speed improvements there. But there's situations where you might not be able to throw hardware at this. So what we did was we took all of our data and we made a handheld imager, kind of like Celebrate UFED out of it. Only just to show how efficient we could be, we made the handheld imager out of a Raspberry Pi. So we were able to take a Raspberry Pi, it's, I don't know, $25, and apply that and run our algorithm on it and collect data. So there's our Raspberry Pi. So let me just show you a little bit about what this looks like. Here's our design. We had a Raspberry Pi 3 Model B+. We had a 64 gigabyte micro SD card. So if we're only collecting the changes, we aren't even collecting full images on here. So we can actually do multiple devices on one SD card. Even if we have a 64 gigabyte phone that we want to collect, we're not collecting a full 64 gigabytes for every time we collect on that phone. So multiple ones could go on here. This is a picture of it. 3-inch touchscreen we put on there, 3D printed case, and you can connect any battery so that you can take it anywhere that'll provide you the 5 volts at 2 amps that you need to run the Pi. Let me just give you a couple more pictures here. So this is another view and a third view. All right. So how did this work? Well, there was a little change that we made, or an addition that we made to our architecture. So the Pi will actually go through multiple states. So there's the state that we connect to a device, and we're out someplace. Maybe we don't have any connectivity at that point, and that Pi will collect the data off of the device. And then it's going to store up that data, and it's going to bring that back. And once the Pi connects to a network, we had it triggering off of a certain network that our server was on. It will start sending the data. It'll synchronize the data with our server. Okay, so in order to do this, I think I mentioned earlier that we use a queuing system to do this. So the queuing system that we use is an open source system called RabbitMQ. And what we're going to do is we're going to add a second queuing system on the Pi. So there's one queuing system on the PMF database that we need. We only need one for our original architecture. On the Pi, we went to 2 queues, and so the data would be stored up in the one queue, and then when it can, it will connect and send over to the server queue, and then the server queue will push it into the database. So that's how we did this. These queues work kind of like a little post office where you're routing your messages through from one to the next as you know the trucks become available to send it over. Okay? So we use 2 queues in this case. Yes?
These Pis are not constantly connecting to the database, right?
Correct. The Pis may be utilized in an area that you don't have any connectivity.
So if that's the case, so they are not aware of what is already stored in the database.
Correct. So that's actually a really good point. What we're going to do is when it goes through that server synchronization, the server is going to sync back the things that it knows about to the Pi. And the Pi, then as it goes out and is utilized during a crime scene or whatever low resource environment that it's used in, The Pi is only going to be able to utilize the things that it knows about and then the things that it learns from the phones that it's acquiring. Okay? The server may know more that it's going to be able to tell the Pi the next time it comes back and syncs up.
So it's kind of
Asynchronous communications.
So if the Pi get a copy of the database to be aware of what is stored, it's gonna fill up the Pi. If the Pi doesn't know that, then it would gonna capture everything because it's not aware of what is.
You may actually collect things twice in that situation, but it's okay if we collect things twice. Once the data gets over to the server will just throw it out and change it to a reference of the data that it already knows about. And then the Pi is going to learn more as it's syncing up with the server.
Okay.
All right, so we have the two queues that will be. This is kind of foreshadowing. It'll become important later. Okay, so let me just show you. This is what the Pi GUIs look like. They're running on the Pi now. Now, an important thing is that there is not a database that's running on the Pi. The Pi is only receiving the hash lists that it needs from the server, and then the Pi is going to add to those hash lists as it collects from other acquisitions. It's not until it comes back to synchronize that it's going to get all of what the server knows. All right. So these are in acquisition mode. It just goes through and it'll add up. It'll add to it. We have a disk space utilized, so we could apply it to multiple devices. This is the synchronization, which once it goes into that server sync mode, when it's connected to the right network, it'll sync with the server. What you actually do is on the server, it's going to come up and we're going to identify this Pi, and then we're going to hit execute here, and all of the data we have our data that needs to be processed. This counter will go up and then it'll go down as it goes into the database. I don't know if you guys saw, but on the video they were using this similar interface, and they had multiple devices in there instead of Pis on the side. Okay, this is the server synchronization. All right. So here's the important thing about this is because of the way our tool works, we can take an acquisition of a device using traditional PMF, the server-based PMF. Then later on, we could take an image with a Pi, or we could even pull in data from another tool. Now it's garbage in, garbage out. If the other tool doesn't give you everything that you want to get, then we aren't going to match it up. That's not a shortcoming of PMF. It'd be a shortcoming of the other tool. But let's say the other tool is going to give you an equivalent image. We could pull that in. These are all go into the system, and we could do those comparisons that we're talking about. We can do that differential forensic analysis that we're talking about off of those images. It doesn't matter how we collected it. All right. Now, let's talk about a different scenario. Instead of acquisition, let's talk about PMF for data transmission. We call it Pablo. There's some sort of acronym. I can't remember it right now. So for data transmission, here's the workflow that some of our sponsors are going through. Even now, we could say that the internet is everywhere. Everybody's on their phones all the time. We have great connectivity. Well, in the digital forensics world, there are some sponsors that there's a phone that maybe is in another country, and they want somebody to analyze it back here in Northern Virginia. They actually put it in a FedEx truck, and that FedEx truck drives from wherever. Maybe I could put a plane in there if it's in a different country. And that FedEx truck takes a while to get there, and then they're able to put it in the database. And I mean, this type of situation still takes sometimes 4 weeks, 6 weeks. I mean, we could do a lot better than that by doing our efficient algorithm. So, very inefficient, causes delays to get to that analytics part. All right, so now Pablo. We've got that same phone. We've got a Pablo client that is in country X. We're going to send it over a satellite transmission, and we're gonna drop it back in Northern Virginia. We're going to transmit a minimal amount of data over this link. This link may not be very, very efficient, or it might have a lot of problems with data loss. It could be one way. It doesn't really matter to us. What we're going to do is we're going to cut down the data. We're going to do our algorithm. We're only going to send the data that needs to get back to the server, and then we're going to reassemble everything on the other side. Okay? Now, I told you, foreshadowing, this whole scenario looks a lot like what we did for the Pi. The Pi is another low resource environment. It's different resources, but we're going to implement this the same way. We're going to take those two queues, and we're going to drop those two queues in here. And so we have a queue on the client side, and a queue on the server side, and then we're going to talk to it. So this isn't as easy as just pointing our stuff at it. We've got a lot of considerations that we need to take into consideration. We have whether the medium that we're sending over is unidirectional or bidirectional. We're going to do something a little bit different in both cases. We have can we stream over data, which is essentially what we're doing with PMF, or is there file-based communications where we need to create a file and then that file is going to be sent over to the other side of the medium? We can operate in both. Latency and packet loss, that's a big one. What we did was we added some forward error correction to our algorithm, so that and it was on our blocks of data that we were sending over. So using things like Reed-Solomon encoding, we could send a set of data, and let's say we lose a bunch of bits of that data. We don't have to get the entire transmission. There's data that is added to it that allows us to reconstruct the original image, or the original data that we're sending across the wire. So if we do have packet loss or latency, if things don't get there as quick, we can use that forward error correction to get back to the original that we wanted to send across. Confidentiality of communications. So obviously we want to do things like encrypt the data as it's sent across the medium. And then in terms of satellites, we got to look at availability of those satellites. The orbits, a geosynchronous orbit as opposed to low Earth orbits, it all depends on when that satellite is going to be available in certain situations. So we have solutions for all of these, and we were able to effectively do this. Here's another example. So now we have fairly high availability over AWS. what if we take our algorithm and we implement this over AWS for inter-region communication? So in this situation, we have the Asian Pacific Osaka local, Osaka, Japan local region, and we want to send data back to our GovCloud instance, which is actually in Seattle, and then we want to pull it down to here. So how do we do that and using our algorithm? Well, we could put our queues in our that we put them in both regions, and then we communicate between there the same way that we would talk between our components in our algorithm, and we pass the data back very efficiently. We think that we can take the process that takes 3 to 4 weeks. We were able to get it down without PMF. We were able to get it down to about a day of sending this over on a terabyte of data. And we think that with PMF, we're going to get down to maybe an hour or two. I mean, very, very quick. Sending data over. So, all right. I think that is the end of the presentation. Is there any questions that I can answer?
What are your biggest finding in doing this analysis? So what did you find so far?
What is the biggest finding?
Yeah.
Well, I think the thing that's been most impactful is our speed improvements have changed the industry, and these commercial vendors are now finding that they can operate a lot quicker than what they've been operating in the past. There's a lot of reasons why they were operating very slow before, and the speed improvements that we've published. We published it back in 2016, and the commercial space has changed because of that. So that was definitely a big reason or a big impactful piece that came out of this research.
Thanks.
Other questions? Thank you, everybody, for listening. On the Mitre site, we have a number of recs for positions in my department doing this type of work. If this interests you, please go out and look for digital forensics and reverse engineering recs on the www.mitre.org. There's a careers tab, and please put in a resume and apply. Thank you.